Hello, and welcome to our next set of stats notes. We are on section 11.2. This is our second to last set of notes for the semester. Last time we introduced the chi-squared distribution. We're going to be using that again this section, so you'll see more of that chi-squared. You really have to worry about the table or doing that kind of work because we'll just use a calculator to get our results. But it will be a chi-squared distribution, so it's important to remember that that's always gives us a positive value, and we always do right-tailed tests with chi-squared. That's going to be true again today. So what we're doing today, we're doing contingency tables and the chi-squared test for independence. So contingency table, so often we'll look at sample data and try to determine if there's association between two variables for a population. So a lot of times we'll be looking at a population and trying to see if there's kind of connection or association between two different aspects of that. Does someone's education level correspond to their income level? Do those things have a correlation? Looking at that kind of thing. The data we usually arrange in a contingency table, which is a table consisting of frequencies. So this would be, the counts, that's what frequencies are. The rows and the columns are categorized by two different variables. So that's our contingency table. The rows and columns are two different variables, and it is all frequencies for the different categories or sets. We call these contingency tables because they are typically used to test for independence of the two variables. We're looking for contingency if they affecting the two variables are contingent on each other if they are connected. In a table where the variables are independent, we can calculate the expected frequency of each cell using the following formula. So since we'll see again that our null hypothesis will be that things are independent, that there's no connection. So we'll use this to create our expected values and to use that to try and test if things are independent. You always start with the assumption that the null is true, so that we just assume they're independent and then compare the expected results if they are independent with what we actually got observed. So we'll use this calculation. We're going to take the row total times the column total and then divide that by the grand total, and that will be how we figure out the number to expect, the frequency for each cell for expected values. Once we calculate expected values, so then we can compare them with observed values in this table, and then we can use that information to get the chi-squared test statistic and do our test for independence between the two variables. So right here, this chart gives the observed frequencies. So we saw that for the two different categories X, Y, and for the two different categories A, B, these were the number you observed. So category X and A, so things that fall in both those categories are 60. So this could be like uses drugs, doesn't use drugs. This could be, I don't know, full-time employment, part-time employment. So like that. So you might see the one category be someone that uses drugs and full-time employed, and the next one be uses drug and part-time employed. So that's something you'd look at is the two different categories and trying to figure out like what to expect in each category. So first off, to do this, we need to figure out the row totals, column totals. So we look at each row and figure out the total. So 60 plus 40, there's 100 in this row. 20 plus 10, there's 30 in this row. If you look at columns, 60 plus 20, there's 80 in this column. 40 plus 10, there's 50 in this column. And the grand total, the sample size is 130, right? You can see there's 130 this way or 130 this way. So that is your grand total they're talking about. And these would be your row totals and your column totals. Okay, so to figure out the expected frequencies, to find those expected frequencies, we're going to take the row times the column and divide by the grand total. So, for example, to figure out the expected frequency, how many do you expect for this XA cell? We take the row total, 100, and 100 times the column total of 80, and then divide it by the grand total of 130. And so we should get about 62 if we round that. So 62 for this one. So 100 times 80 divided by 130. To do this one, I do my 100 for the row times 50. 100 times 50 divided by 130. So this one should be about 38.5, or just round it to 38, because 38.4 would round to 38. This one, the row of 30 times column of 80. I don't know why I keep hitting multiply or enter before I divide. You could just type the division, divide by 130. You can type the whole thing in at once, that works fine. So 30 times 80 divided by 130, and this one should be 18. And then this one is 30 times 50. Oops. Let's try that again. 30 times 50 divided by 130. And we get 11.5 or 12. So these should mostly get you the same amount here. So you see 18 plus 12 is 30. 62 plus 38 is going to be 100. There might be a little bit of error due to rounding, so you might be off by 1 or something. That's okay. But that's the idea. So this is the already printed numbers were what they observed. That's what they got from their sample result. And the red numbers are our expected. So based on this data, we were able to kind of calculate what we should have expected if they were independent. If these variables did not affect these variables, if there was no connection, these would be the values we'd expect based on just how much was in this row, how much is in the column, what would we expect. And then you look at the difference between what we expected, what we expected and what we actually got. So you can see how here we were expecting like 62, but we got 60. So there's a 2 difference. Here we expected 38, but we got 40. And so we look at that change, that difference between what we should have expected for the each of these cells versus what we actually got, and that's how we compare. Is there actually a connection between these different variables? Or are they independent? Are they close enough to this to be independent? The closer they are to these results, more likely we'll say, oh yeah, they're independent. They don't really affect each other, the 2 different variables we're looking at. Okay, so that's the idea. That's the basic setup. So we are going to be working with charts like this. The data will be given as a chart, and that's going to be one way you know what you're doing. You'll see the chart and say, oh, this is that independence test. This is where we have to figure out the expected values of that. Actually, the nice thing is when you do the independence test, it does figure out the expected values for you, but you should know how to do it just in case you need to just figure out the expected values. Okay, let's look at the independence test. How does this work? So it is a chi-squared test. So this independence test is a chi-squared test for independence. So it does have a chi-squared test statistic. Thankfully, we'll just kind of let the calculator calculate that because it is a process of subtracting, squaring, dividing, and adding all up all these different values. So we'll leave the calculator to that. One important thing to know about this is the degrees of freedom for this test. The degrees of freedom is r minus 1 times c minus 1, where r is the number of rows and c is the number of columns. So the number of possible values, it's going to be your rows and columns. R rows, c equals columns. So to find the degrees of freedom, we're multiplying 1 less than the number of rows by 1 less than the number of columns. That's what we're doing to get that degrees of freedom. Okay, when you do this test, the null hypothesis, so null is always they're not associated, or we would say they are independent. So there's really no connection between the two. So for the previous example, I said, whether or not you smoke and whether you're full-time or part-time, if they're independent, we find out that your smoking status has no correlation to your part-time, full-time status, and vice versa. That'd be independent. Alternative hypothesis for this will always be that they are associated. So there's only one option. It's always going to be that they are associated, that they're dependent. So this would say that, yes, your smoking status is associated, is connected to your full-time, part-time status. We don't know which one causes which. This is not a causality type test. So I can't say that whether or not you smoke causes whether or not you're part-time, full-time, but I can show that there's a connection between the two. That's what this would do. The best it would do is say, yeah, there's some kind of connection. There's actually a link between your smoking status and whether you're employed or full-time or part-time. There are requirements for this, typical requirements we've seen. Data has to be random. You have to have data in a two-way table. That's what they call that chart that they got. So it's going to be given like this. They should have data in a two-way table. And then the expected frequency should always be at least 5 for every cell. So when you do your red numbers like I did here and find the expected values, if any of those are less than 5, then you have to go back and try again. Use a bigger sample size, basically. That's their test statistic. Again, we'll let the calculator calculate that for us. You can do both critical value and p-value method. We're not going to worry about critical again because that's something we don't really need. We'll mostly just use p-value because you can do it in the calculator. As always, compare the p-value with the significance level and reject if the p-value is small. So if we reject, that's when we support the alternative, and that would mean that there is association, that they are dependent. So if we reject, that means that they are dependent. There is a connection between the two variables. So if you have enough evidence, you reject the null. You say, I don't believe they're independent. I believe that they are dependent. So you're always assuming they're independent to start with and trying to show some kind of dependence between them. And that's kind of the general way to do it, right? We assume at first that there's no reason why these two variables would connect to each other until we can provide evidence that they are connected. They are affecting each other. So let's do a test. Let's do a test at the of independence using this. So to do this test, they're going to give us a chart like this. First thing to note is we're not going to use all the data in here when we put it in our calculator. We are just going to use this stuff in the middle, because the stuff on the outside edge, you'll notice, is just totals. So this is what we're going to be using. We'll actually put this in as what's called a matrix or an array. So put that in the matrix A, and this will be the data we put in there. We don't want to include the totals when we do this. Okay, so note that, like I said, null. The null hypothesis is that they are independent. The alternative hypothesis is always going to be that they are dependent. There's a connection between the two sets of variables. So like here we're looking at diabetes and not having diabetes and the amount of school you finished. So we're trying to test and show us if there's a connection between whether or not you have diabetes and your school, what completion rate you have with school. We won't be showing which one causes which, so you don't know if like your school completion would cause the diabetes or vice versa, or if there's some other third-party variable. But we're going to test to see if there is some connection between those. Okay, to do this, we're going to do a chi-squared test. So if you go to your calculator, go to stats, go to tests, we are going to be scrolling to the bottom, and we are going to do the chi-squared test. Not the goodness of fit test, we're going to be doing the chi-squared test. And then to do this test, we're going to have to enter some data. We're going to enter data in A and B. So the observed data is going to be the data you're given. That's going to go in A. The expected value is going to go in B, but the expected data we don't actually enter. That's going to be like filled in for us. So don't need to enter B. Calculator fills it in. So we really just do A. Okay, so how do we do A? So we're going to hit, instead of the math button, we're going to look at below it, have that matrix button. So we're going to go to the matrix button. We're going to hit second. Oh, I'm going to quit out of this. We're going to hit second matrix. And you'll see the first one is A. We're going to hit enter on A. Sorry, not A. We want to do edit. Second matrix. It's been a little while since I did this. We want to edit A. I forgot to scroll over to edit because you want to edit it. First thing you want to do is you want to tell it the rows and columns. It is rows first and columns second. So to do this, we'll do matrix, do edit, and we'll do rows times columns. So here I would want 2 rows. So we put 2 in there first, so 2 rows. And then I want 4 columns, so 2 by 4. So for this one, I would want 2 by 4. And type that in. So I type in 2 by 4. And again, I don't want no totals. Don't want to enter those totals. All right, so I'm going to type this in. I'm going to type in 45, hit enter. Notice it goes across. So next I'm going 20, enter, 24, enter, 19, enter, 258, 26, 399, 355. Okay, so I'm just entering the data as given. So I type that in, just like we had the data at the top. I'm typing in here. Once I've got it in the matrix, then I'm ready to do my test. So once I've got in the matrix, I'm going to go to my chi-squared test, hit enter. So matrix A is filled in. Like I said, matrix B you don't have to worry about. That'll fill itself in. You just have to have a different matrix letter there besides A. It's that way it has somewhere to put the data. So that's why we put a B there, but it could be C, D, whatever. We're just going to leave it A and B. Hit calculate. The really important was the data we put in A. Hit calculate, and it gives us all the stuff we want to know. So it gives us the chi-squared value, which is 30.17. And it gives us a p-value of 1.269. It tells us the degrees of freedom, which we didn't figure out for ourselves. So, but if you look at this, you notice that the degrees of freedom would be, there's 4 rows, so that's 3, because there's always one less. Sorry, 4 columns. So 3 times, and then there's 2 rows, 1 less than that is 1, is 3. So that's how you figure out the degrees of freedom. I did, columns by rows. It doesn't matter because multiplication, you get the same answer either way. But that's the idea. So they did a lot of the heavy lifting for us, right? Because we didn't have to sit there and figure out all the expected values. We didn't have to sit there and do all the calculations. Thankfully, the chi-squared test mostly does all that for us. All that, repetitive, kind of tedious calculations. But what really we needed is it gave us the p-value, which I forgot, this is times 10 to the negative 6. So this one is such a small value. I think this ends up being 0.00000012345 that's actually the p-value. I guess I picked one where it's very not very low p-value. This is a really small p-value. So we compare that really small p-value with the significance level, which was given at 1%. So that's our level, 1%. So compare that with 0.01, which of course it's much smaller than. So the p-value is smaller than the alpha significance level. So we reject the null. And again, if you have enough evidence to reject, then you can say the variables are dependent. So we've actually showed in this case that there is a connection, a correlation between your diabetes status and your education level. Again, I just made up these numbers. These aren't real or anything, so I'm not saying anything about anything, but I just want, this example, that's what it's showing. The example is showing a connection between these two different sets of variables. And that's what we use this for in real life. As we look, is there some kind of connection between these? We didn't show causality, so we can't say which one causes which, but we can show a correlation, a connection. So this is using that chi-squared test. That's the test for this, not the goodness of fit test. Like I said in the last notes, the goodness of fit test shows up on some characters, not all of them. Thankfully, this chi-squared test is on all the TI-83s and 84s. So if you have either of those, you should be able to do the chi-squared test. So that's the idea. You just have to type in the data, not the totals, into matrix A, run your chi-squared test, and then just use your p-value to do your comparison. Now, one more thing to show with this, so not a whole lot, one more thing, is the test of homogeneity. So for independence, we look at one population and we look at 2 different variables. For a test for homogeneity, we do something different. Instead of studying one population, 2 variables, we study one variable across multiple populations. So for homogeneity, we look at one variable across multiple populations. So we might look at whether or not people are diabetic, but we might look at multiple nations and see if there's an equal percentage or distribution of diabetes across these nations. And then we could maybe look for, maybe there's some nations that have more or less, based on that. So you could look at the level of education, but you could look at the level of education across several nations instead of just one nation or several states. We use the same method, so the test is going to be the exact same. It's just that you'll notice instead of doing 2 different variables on one population, we'll have multiple populations and just look at one variable. So we'll go ahead and do this problem. Here they have multiple populations, different countries, and they're looking at whether they are employed or unemployed. So they have one variable, which is employment, with lots of populations. So these would be your populations. Okay, we're going to state the null and true hypothesis. Following example, we have 5 states, their populations, look at the employment, and then we'll do a test. I don't think I said what level, so use the following table to determine the proportions. It's different across states. I should have said a level on this, which I think I forgot to. So we'll say at let's go 10% level. I don't know. So I should have stated that. I don't know why I didn't state that. So I should have stated that. But let's go ahead and do the test. Okay, so to do this test, again, we're not entering the totals, we're just entering the values. In this case, it actually didn't give the totals. So we are going to use this whole chart, because there are no totals on this chart, and that is going to be our matrix A for our chi-squared test. So again, our observed values will be matrix A. Our expected values will be matrix B, which it'll do for itself. It'll calculate that for itself, so we'll reset that. So you have to go back and clear, but we do need to enter this data into the first matrix A. Second matrix, go over to edit. We have to determine the size, right? So this is 2 by 1, 2, 3, 4, 5, so 2 by 5. And then type in the results, so 488, 362, 32, 166, 89, 208, 113, 9, 68, 43. Oh, I made a mistake somewhere. It's supposed to be 2 by 5. Okay, I gotta try over again. 38, 362, 32, 166, 89, 208, 3, 9, 68, 43. Okay, now it's in there right. I was going to make sure your data matches your chart. Somehow I missed it. I got 4 instead of 5 in there. Okay, so now this is good. I'm going to do stats, tests. I go up to get to the bottom because it's closer to the bottom. So that's how I keep going to the bottom fast. I just press the up button and it jumps all the way down to the bottom. Chi-squared test. A is what I want because that's where I put that data. Calculate, and there we go. So we get our values. We see that the chi-squared is 7.656. Again, chi-squared tests are always right-tailed tests, so we're always looking for this chi-squared number to be big enough. The bigger the chi-squared, the smaller the p-value, more likely you are to reject. This one's not very big. You'll notice, we only got 7.6 versus the last one where we got 30. And so this one actually is not as good. You can see the p-value here is pretty large, right? 0.105. It's like 10.5%. That's pretty high p-value. Degree of freedom with this one would be 4. Notice because we have 5 columns by 2 rows. So if you 5 minus 1 is 4, 2 minus 1 is 1, 4 times 1 is 4. So that would be that. But as always, we're going to compare this. We'll compare p-value with significance level. And even at the 10% level, because our p-value is 0.105, that's still bigger than 0.10, than the alpha of 10%. So this is bigger. And again, if the p-value is too big, we fail to reject. Remember with failing that we never actually show something is true when we fail. We fail to show, we can't show dependence. So you'll never prove that things are independent. That was kind of the assumption to start with. We can't prove from the assumption that we made. We assume they're independent, and then we tried to show that that's false, that they're actually dependent. And so in this case, we were unable to do so. We couldn't show that they were dependent, and that's all we were able to do. So we didn't show they're independent, but we were unable to show that they're dependent. In this case, we're not able to show that there actually is a difference across these different nations in their employment rates. So can't show dependence, so can't show difference in the employment across these states. So if I was trying to show that some states had lower or higher employment, I wasn't able to show that. There's not a significant difference from one population to the next on employed versus unemployed. They're too similar, so I wasn't able to show that. Okay, so that's what this section is all about. It's these tests where you're going to be given a big chart. That's the nice thing about this section is it's really easy to know when you're doing a problem for the section. So when it comes to the quizzes and the tests, you can really identify these right away because you'll see this big chart. And then if you see the big chart, you're just going to put the observed data in option A, do your chi-squared test, and bam, you got your p-values. You can see whether or not to fail to reject. And that's really what it comes to this section. We've got one more section left, our last section of the semester. as the last couple sections have been, you've seen, it's going to be one more of these where we just throw it in the calculator and really let it do the work for us. The biggest thing, hopefully, you've seen on this test is that you're going to need to know which calculator buttons to use for which problems. So when it comes to the test, the last test, you should be thinking about little notes on your 3x5 card that help you remember, which calculator test for which problems. How do you identify those problems and know which one to do? So use that practice exam as a chance to kind of sit there and think, okay, how do I tell which problem this is? What's the key things I look for? Like it's the chart on this one, or if it's a terminology. Look for those keywords so you know which function on the calculator to use. Okay, I'll see you on the next set of notes.